Hey, what's up guys, my name is Cherno and welcome to episode 10 of the Sparky game engine series in which we make a game engine from scratch in C++ and OpenGL. So this is episode 10, okay? Every 10 episodes we're going to be doing a maintenance episode. What that means is basically we're going to be going through the code, doing somewhat of a code review and essentially making sure that the engine is more or less okay. We might be doing some refactoring, which means we might be moving things around and changing them and just basically not really adding new features but maintaining the code and whatnot. So what's going to happen as well with that is we'll also basically blend in an optimization episode into every 10th episode. Because this is basically what's called a I guess a maintenance slash optimization episode, I'm also going to kind of combine a Q&A kind of video into it. So what I've done is I've basically put the chat onto the video so you guys can see what's going on, because this is being streamed live. And what happens is when I do stream stuff live like this and then I put them up as a video on YouTube, people just don't have the context of what questions I'm answering and all that stuff. So I thought it'd be good if the chat is actually in the thing. So yeah, so chat is being recorded. Hopefully they behave themselves. But keep in mind the chat is a bit delayed to what I'm saying because there's about 20 seconds or 30 seconds to stream delay. But that's the idea. So the chat is going to be in the video because we're going to be interacting with them somewhat. And the chat will only be every 10th episode. So in other words, every maintenance slash optimization episode, the chat will be in the video, okay? So it's not like a new thing that we're doing. It's just going to be every 10th episode. All right, so let's talk about this. So this is what we had last time, episode 9. It worked pretty well. We saw that it was running smoothly with 57,000 sprites, which is the dream. But unfortunately, the problem was, well, there wasn't a problem, but we had no way to measure the performance. So what we're going to do today, apart from maintain our code and whatnot, we're also going to add some kind of performance measurement thing, right? So I want basically an FPS counter kind of timer class so that we can essentially I guess measure our performance pretty quickly and display what our frames per second are. And I'm also going to introduce profiling in Visual Studio in this episode so that we can measure performance and whatnot. So basically there will be quite some I guess we'll call it this will be a pretty long episode in which we don't really add anything new, but it'll be a maintenance episode. I've said that already. Let's begin. So what we'll do is let's see. Okay, so we'll get rid of the printf now. So I think we'll just start off with making a somewhat like a timer class, okay? So we'll go ahead and this isn't really a graphics thing. It's going to be in utilities. So in utilities, I'll add a new item. We can probably just make it header only as well. I'll just call it timer.h, okay? And inside timer.h, we'll go ahead and I think we'll just, we had file utils. Was that in utils? No, it wasn't. It was just kind of sitting here. So we'll go ahead and say, so class timer. Okay, so we'll just, for now, because we're supporting Windows at least, we'll just use the Windows header for this. So I know you guys are going to hate me for using something that's Windows only, but whatever. If you're on Linux or whatever, you can just use like timespec and other classes like that. We're going to be doing this instead. So we'll have a large integer. See, this is why it's fun to use Windows header stuff. You get awesome names like large integer. So we'll get stuff like large integer, which is always just the best. So we'll have so we'll have a start for the timer. So basically what will happen is when you construct this timer, this will probably make more sense. When you construct the timer, we'll just make this header only as well, at least for now, because this won't be something that we use actively in our game, probably. So when we do start our timer, we will basically set our start to be. So if we query the performance counter towards start, so we'll be using query performance counter and all of that cool stuff. We'll make a large integer called frequency. We'll query the performance frequency. Yep. With me so far. And we'll make our frequency, which will be just a double. So the idea is if we divide something like this, it'll give us the proper kind of part. So frequency equals 1 divided by frequency dot quad part. Okay. All right, cool. So there we go. That is pretty much all we need to do when we initialize the timer. Now, other stuff we will probably do is, I don't know, we'll have a reset. We'll just have a reset, and then we'll have like a way to get the elapsed time. So float elapsed will generate elapsed time, reset will reset that to 0. So basically, that's probably all we'll have now, honestly. So reset will set the start to what the current time is. Yeah. So if we just do this, that is kind of pretty much all we need to do. And then elapsed will actually work out how much time has passed since like last time. So since start. So if we make a integer called like current, we'll query the current time. And then we'll just, okay, so we'll need to grab the difference. So if I just go, we'll need to probably use an int64 as well. Cycles, so that'll be current dot quad part minus the start. And I think we could probably just return cycles times frequency variable, which should be correct. I think that's right. I don't know. We'll see. Oh, and we need to make sure that's the right. Thank you, stream. See, so now you can see how the stream is helping me, instead of just being like, oh, I can't see the chat, lol. So, anyway, there we have what looks like an average timer class. I mean, it's Windows only, but it should be good. So if we were to test this, for example, we should be able to just say, timer.h, timer. This is in utils. So that initializes it, obviously, and we'll do that outside of, sorry, I can probably bring this down here. We'll do this outside of our window and whatnot. So we need to reset our timer at the beginning of every frame. And if we like, we can probably just grab the elapsed time, say, at the end, and that should give us our performance in milliseconds. Okay, so if we were to, actually, no, it won't. Will it? Yeah, it will. That'll give us our performance in milliseconds. Okay, good. So, let's just try this out. So we'll use printfs. Printfs are generally a bit faster than cout, but also they enable us to just quickly append text and stuff without having to have a million things. So let's see if this works. Yeah, that's not right. That's a little bit weird. Oh, I'm not resetting. Oh, well, I mean, I don't really need to, but we should probably be resetting that as well. And means that I don't need that. Well, I mean, it was doing that before anyway. I don't, current cycles, yeah, my start. Yeah, okay, we'll get rid of that. I don't know. I was resetting it anyway. Yeah, I mean, well, okay, so if I don't do that. Oh, there we go. That's the elapsed time. Good. So we do need to reset it though. So if we reset it, and then we grab the elapsed time, that should be since the reset. What does reset do? That should work. I'm actually kind of surprised it doesn't. Like, that's way too low. Oh, unless it's in seconds. It probably is in seconds, lol. No, it's not. Yeah, it's not really. Okay, let's take a step back, stop guessing, and actually go through this. So we've got our frequency. Oh, okay. So let's change this up a little bit. So we've got our frequency. If we just say, so it is in seconds. People are saying it was in seconds. Okay, I don't know. I mean, yeah, okay, I guess that seems a bit right. It seems like it's being capped at thingy. I think we should probably, I think we should probably just, let's try it with this. This should work. So this should be like, I don't know, a lot. Yeah. Oh, yeah. Okay. So it seems to be working. Everything is good in the hood. Okay. So now, if we want the FPS, we've got a few options. So those are milliseconds per frames, right? If we want the FPS, we've got a few options. The best way, well, there's several ways, but what we could do is basically, we could have, let's say, we could have just we could have just like the current time, yeah? And what we would do is, time is just going to continue increasing, okay? So what we can do is we can basically get the current time, yeah, which is time.elapsed, and we could say time.elapsed minus, if time.elapsed minus, say, I don't know, some kind of timer variable we have, which we could just make large integer t or something. I'm running out of variable names. Minus t is greater than 1,000. That's an integer. And we could just say something like t plus equals 1,000. We'll just make it a float. Okay. So if it's greater than 1,000, and we'll add on 1,000, then we need to, that will basically happen once per second. Except for the fact that it already is put once per second, not milliseconds, so that should work. And we should add on 1 second. So I think this should happen once per second. So let's just printf hello, just to verify that my timer is working. Set that up. Probably should do it on the fast one. Okay, it's definitely working. All right, cool. So anyway, there we have. So this really should be called timer, but doesn't matter. We've got our time. So yeah, we don't really need this anymore if we don't want milliseconds. So I can really just get rid of timer. I'll call this timer. We'll just have time. We won't have this, and then all we really need to do if we wanted to count the frames is we might have something like an unsigned int frames equals 0. It doesn't have to be unsigned or anything. We'll just have normal frames. Equals 0, then we'll go frames plus plus. We'll subtract the timer from that, and we'll just say we'll print out. So we need to reset frames. So this is once per second. So of course, since it's frames per second, we'll reset it back to 0. We'll pop in frames or FPS here, followed by our integer, and there you go. That should be frames per second. So if we look at that, we should be at 60. Okay, I'll accept 54 as well. We are running in debug mode. Okay, cool. And then this should be like 4 or something once it stabilizes. True story. All right. Stabilize. All right, there we go. So it's about 6. Cool. I'm okay with that. All right. Anyway, that is our timer out of the way. Okay. So one thing I should note is we are about to be testing performance. That's kind of half of our goal this episode. So it's kind of a bad idea to test performance in debug mode because nothing is optimized. Everything is basically configured so that it's easy to debug. So what we should do instead is basically use release mode. To do that, we'll have to configure release mode properly. So if I go into properties, you'll see that like we've only done debug mode, we've really never done release. So let's start with basically copying across many of the properties we have here into release. Our output directory should be the same. So make sure that's good. Yes, we'll save. So we'll go back to debug. We'll copy our intermediate directory. We'll just make sure everything is pretty much the same. I could just put it into all configurations, but I'm deliberately not doing that. That looks good. These directories, we'll have to make sure they're copied. Otherwise, it probably just won't build. So I'm just making sure everything is the best. Certainly looks like it. Yes. Okay, debug, well, no, that's not what I'm looking for. I'm looking for linker. Okay. So, if we now switch our mode into release up the top here, okay, from debug into release, and we just hit F5, okay, I forgot to copy the preprocessor definitions. As my stream is pointing out. Okay, let's grab preprocessor from debug. One thing I forgot. Okay. So now it should totally build and work. All right, cool. You can see our console's even a bit smaller. Let's increase that back up. No. What did I have it on before? Like 24-ish? That's probably big enough, right? Okay, cool. So now you can see, okay, so, and it's at 60, so good, performance is better. We have not optimized this yet, though. If we go back into release, there's a few things that we want to set up, okay? Particularly in the optimization category. So optimization is set to maximize speed, that's good. Inline function expansion, we want to set that to any suitable, so it will basically inline as much as possible. Intrinsic functions, yes. I mean, that's the default anyway. Favor size or speed, we want to favor fast code. Okay, that's important. What else? Optimization, yes. Okay, in code generation, in the floating point model, we want to use fast. And then enhanced instruction set, we want to use simmed extensions too. We'll actually, so for those of you who don't know, simmed, or I don't even know what it stands for. I've forgotten. This is embarrassing. But streaming extensions, basically. Single instruction, multiple data. Yeah, okay. So simmed extensions is what I should say. Basically allows you to, well, it allows the processor to act on stuff simultaneously, right? So basically you get 128 bits. It depends on the simmed. Sometimes you can get 256 or 512, but the idea is usually it's about 128 bits and you can execute operations to multiple data in parallel. So say you've got 4 floats, right? A float is 32 bits, you've got 4 of them, that's 128 bits. So you could, for example, multiply a vec4 with another vec4 in one CPU cycle, essentially, because it will do it in parallel. So simmed is very important. Like if we were really critical about speed, we would be using simmed for pretty much all of our maths. The reason we're not doing that is because, so as the name implies, single instruction, multiple data, it only works, okay, well that name doesn't really give away too much, but basically single instruction means, you know, if we want to have one instruction such as multiply for multiple data, such as, again, if we're multiplying 2 vec4s together, we just need to multiply each component to each other. It can execute that in parallel very, very, very quickly. So essentially, it's like one operation. So it'll be 4 times faster, because instead of doing 4 separate operations for each component of the vector, it will just do it all at once. Very, very quick. It usually makes your maths code about 4 times faster, just simple as that. The problem is, yeah, so we would be, if we were really critical with speed, we would be using simmed instead of multiplication, for example, for our matrix classes and vectors and all that stuff. The reason I'm deliberately not doing that yet is for 2 reasons. One, I don't want to confuse myself and you yet. But B, we will be trying to get Emscripten to compile this into JavaScript and for it to work on the web. And I don't think Emscripten is friends with simmed. So yes. So I don't think that is the best idea yet. Eventually, when we have some spare time, and maybe in future optimization episodes, we will definitely do this for desktop games. Okay, so for desktop implementations of Sparky, we will enable simmed, and we'll actually, I mean, it is enabled, but we'll actually do it ourselves explicitly and whatnot eventually. But for now, no. Okay, anyway, that should be about it. So if we just hit OK and we build this, one thing you should note is that in our directory now, outside in Sparky, we should have bin, and then now you'll see that there's this thing called release, and it should be set up the same way as debug, and it looks like it is. Okay, cool. So if we launch this, we should be running much faster. Of course, we are being capped by vsync at 60 FPS, which means that it can't go above 60. It's much bigger than 60. So we need to turn off vsync. Luckily, it's relatively easy to do in GLFW because they've pretty much done it. So all we need to do is, in the window.cpp class, we will be like glfw set interval or glfw interval, glfw swap interval. We'll set that to 0. Okay, if it's 1, it means it'll be at 60. 0 means it will be turned off. So now we're not locked. And you can see it's running at about 700 frames per second. Okay, which is crazy fast for rendering 50,000. I was going to say 500,000. 50,000 sprites. Okay, yes, they're not textured, but no biggie. Okay, 700 FPS, 50,000 sprites. That's good. And the other thing I should probably note is that our memory usage using this batch renderer is 27.8 megabytes for 50,000 sprites. Okay, 27.8 megabytes. If we take a look at the other renderer, which is our simple 2D renderer, which has one draw call for everything, you should see a spectacularly different result. Okay, Let's just wait for this to stabilize. Okay, so you can see with release mode, by the way, it's running at 15 and not like whatever it was before, so it's kind of usable-ish. But our memory usage is 297 megabytes. About 300 meg. Yes. Yes, that's not good. Because it's queuing up all of those things and it's being... not very nice, okay? So that's something to note as well. Not just performance, memory usage. 300 megabytes is a lot. 300 megabytes is probably what you'd expect from a game like this. Just for everything, though. Not just the sprites. So, yes, this uses 27 megabytes and it's much better. Okay, cool. Apart from the fact that it runs very fast, as you can see. So that's very, very, very cool. Now, let's continue on. So one thing I want to mention as well is we should probably talk about profiling. So now that we've gone ahead and we've implemented a timer class so that we can actually do this, let's actually take a look at the Visual Studio profiling tools. Release mode is a good place to do this in. Make sure you're in release mode. The problem with profiling in release mode, though, unfortunately, is all the inlining, okay? Inlining will make it difficult to debug certain performance, like, boundaries, basically, and bottlenecks, but we'll try our best anyway. So the way we profile in Visual Studio, and luckily this is included in Community Edition, but under Analyze, you'll see Profiler, okay? We want to basically hit Analyze, Profiler, and you probably won't see this. I've actually done this before on this project, on stream, but outside the videos. So this will probably be, unfortunately, set up for us. So if I quickly just open up... I'll try and reset it to what it should be for you guys, because it won't look like that. View... If I can only find it. Maybe it's under debug windows. No, it's not. View. Where is my profiling stuff? Other windows. Nope. Whatever. I'll just if I hit like new performance session, it'll pop up. So performance. So I'll basically delete all of these. Okay, and it should. This is probably what it will look like for you. So if you hit analyze. Profile, okay, yeah, so start with profiling pause and stuff will be not good. So if you go analyze, profiler, and then new performance session, okay, under targets you can add target project, so it'll add Sparky core. And now that you've done that, you can basically either go analyze, profiler, start profiling, or under actions it'll also be here as well. So we want to hit start profiling with start with profiling paused. The reason we do that is if we don't, it'll basically profile all of the... We basically want to start profiling when it's actually running, okay? What I mean by that is, and stream needs to calm down about the turkey, by the way, because I am cooking a turkey right now, but it's totally fine. It's definitely not burning. I mean, I'm the Cherno. I don't burn turkeys. I professionally cook them, so they're fine. Don't worry, chat. Don't worry. Yes, so we want to start profiling when we're actually playing the game. And the reason we do that is because we don't really want to, well, in this case at least, we don't want to profile this for loop that adds 57,000 sprites, right? We want to, we don't want to profile that. We just want to profile the actual rendering performance, which is why we don't want that extra data floating around. So if we start with profiling paused, you might have to accept like some kind of, you probably need administrative permissions for this. If you just hit, once it's running, if you just hit resume profiling, it'll start gathering data, so you might want to play around with it, make sure everything's running well. This is our batch renderer, by the way, but make sure everything's running well. Yeah, it looks pretty good. Let's hit stop profiling. You can profile for as long as you want. I think that's probably enough samples though. All right, cool. So we'll wait for this to prepare and open the report. Hopefully my face cam and whatever will not hide this too much. If it does, I can just pop it out, so don't worry. Okay, cool. So, okay, this is great. So if we look at this, one of the bottlenecks, I'll kind of show you how to read this because it can be a bit weird to read for if you've never read these things before, but this is our CPU usage, this line. It's not that useful. I mean, if you go into stuff like so this hot path is basically, as the name implies, hot path. It's basically where, so the hotter something is, the more time it takes, okay? So NVOGLV32.dll is NVIDIA's OpenGL driver, okay? So basically that is taking up 30% of our time, okay? Main is taking up 99% of our time, which I would hope would be the case because it's all we've got. But inside that, the most expensive operation we have is actually calling functions in NVIDIA OpenGL, which is good because that means that our OpenGL calls are what's taking up the most time and not our code, which is probably good. Now, if we click on this, again, this might be a bit difficult to read because it's in release mode. But if we click on main, for example, this isn't too bad actually. Let me move this stuff over a bit. If I'll pop it into. Oh, I can't. It won't let me pop it into these things. Okay, I'll pop this over here. And then I'll just drag this like this so that it's not being taken up by the face cam. Okay, cool. So this is the profiling stuff. This is our startup stuff. Cool. This is our main. So we see that the function body, whatever. So the function body itself takes up 58%. But from there, these are the functions that get called. As you can see, you might expect our stuff like renderer.begin or renderer.submit or window.update to get called, but they don't because they've been inlined. So it's a bit difficult to, that's why I said it's difficult. So I'll pop this into debug mode in just a second so that we can actually see our stuff in action. But we can see that the biggest bottleneck in our performance right now is actually renderer.begin is surprisingly quite big. And I'll tell you why. It's because of the binding. But 57.4% of our stuff, and this isn't just of like this is of our entire application. So 57.4% of our entire application is spent on submitting these sprites for rendering. You'll see that the actual rendering of them, because it's one draw call, is 0.3% of our time. Okay? Window.update is taking up 11.6% of our time, so that's swapping the buffers. That is absolutely fine. Not something we can control anyway. We can control all of this stuff. So render.submit is the biggest thing. Now, if we try and go into there, you can see we can't because it's been inlined. So we'll tell it not. Actually, we don't have to go to debug mode. We can just tell it not to inline our code. We'll do that in a minute. But the idea is that's basically the gist of how you can read these things. As you can see, it's incredibly useful because you can see exactly the more red something is, the more expensive it is, right? The more time it takes up, the more samples it takes up, right? If you go into call tree as well, you can see exactly what's going on. So inside main, unfortunately, again, it's really hard to read because it's inlined everything and it's basically going straight to the OpenGL driver. So yeah, I don't know why I closed that. Whoops. No, here it is. Okay, so yeah, which means it might not be that good. Which is why our functions, you can see, the only function we run is main because everything else has been inlined. So we'll definitely pop out of that in a minute. I don't think anything else will be too useful here. Okay, but that's the idea. So it's really important to do this stuff because you can see exactly where your performance is being spent. Let's go ahead and stop the inlining madness. So if we go into our Sparky core, we right click on this, we hit properties. Under release mode, if we go into optimization, and you'll see this inline function expansion, we did change that to any suitable. We're going to just put that to disabled, which means that basically the compiler will not inline functions. So inlining is the process of basically getting rid of the function call by just pasting its contents into the path. So for example, render.begin does this stuff. So what it will do is it'll just kind of take this stuff and just pop it here and replace the function call, because that means it doesn't actually have to call a function. Okay, so that's kind of what inlining does. Very, very broad kind of definition of what inlining does. If you want, you can research it more, but that's the idea. So if we get rid of inlining and we go ahead and under our Performance Explorer, which is hidden over here, if we go ahead and go Actions, start with profiling paused again, and wait for it to recompile our code with the new optimization properties we've given it, play around with it a bit, you can see how much slower our code is, first of all. Yeah, you can see how much inlining really does. The reason it helps so much is because we're iterating through 57,000 sprites, which means that it's doing 57,600 function calls per frame. We just got rid of that, basically. We just got rid of 57,600 extra function calls by inlining them, okay? Very important stuff. But anyway, let's go ahead and hit resume profiling. We can probably get rid of this now. I'll pop it right over here at the end of my face cam. Resume profiling. So inlining is important, but again, it kind of doesn't help us performance tune. Oh, I shouldn't have done that. I dragged the window. Ah. I dragged the window, which would have stopped it and messed up all the data because it would have paused. Let's get rid of that. Delete. Okay, let's try that again. So I'll start with profiling paused. I'll resume profiling. I won't drag the window this time. We'll play around with it just a little bit. And should be enough. Okay, so we'll just go back and we'll stop profiling. Now we should see some slightly different data. Okay, so yes, you can see that now instead of NVIDIA OpenGL, we see this. So if we click on main here to go to this, we should see something quite different. Instead of this stuff, you can see the called functions, since it's not inlining, are actually our functions, which is very, very good. So you can see that in this thing, by far, renderer.submit is first of all taking up more than 54%. Does that mean that everything else is running faster? No, it just means it's taking up less because it was inlining it. So renderer.submit is taking up the most. So if we click on submit, we can see exactly what is going on here. So yeah, most of this stuff we kind of can't really avoid. We can avoid it by not doing these mathematical operations are pretty fast. I'm not going to say that they're our bottleneck. Really, we could... one of the biggest bottlenecks is probably the color, just because it is a vec4, whereas we could just have it as an unsigned int, for example. I honestly think that's probably... yeah, that's definitely hiding... that's definitely taking up a few frames. Or I should say a few milliseconds overall, and yeah, a few samples. Okay, so we can probably get rid of that and change that. We'll play around. Okay, we'll since this is an optimization episode, we'll go ahead and refactor color to be an unsigned int, and we'll see if that works better. So anyway, that being said, the point is we can see exactly what's going on here. So it's seeming pretty good. And again, it should be pretty good because it's our batch renderer. I specifically wrote it to be pretty good, right? I didn't write it to be terrible. Now, I know what you all want to see. You all want to see what is the bottleneck of our batch renderer, or of our not batch renderer, I should say. So let's go ahead and start with profiling pause again. This is our old renderer. Let's wait for it to stabilize. I don't know why the first few frames are very slow, but let's resume profiling. Yeah, it looks pretty good. Stop profiling. Okay. And here we go. So, now you can see that before submit was taking up the most time, now flush is taking up the most time. So if we click on main, just so we can see exactly what's going on, submit is really taking nothing. Is that good? Are you suddenly like, oh, well, submit is taking nothing. That means submit's really fast. The answer to that is unfortunately no. Submit is no faster than it was before, right? Submit, well, it actually might be a bit faster because all it's doing is queuing, but my goal here, or my point, is that it's not necessarily faster, it's just the other thing is taking up much more time, okay? So you have to be kind of smart when you read this, and you can't just assume that, oh, okay, less numbers equals better, or more numbers equals better. It's just, it's a percentage, right? It's not a millisecond count, it's just a percentage. So, of our time spent total. So 97.8% of our entire runtime for our game, or our game engine, 98% is the flushing. So what on earth is going on in there? Let's try that. Flush. Well, draw elements is taking up 30%, which surprisingly isn't even that much, right? You'd be like, well, out of like 90%, I assume this would be taking up this much. If we go back for a second, so flush. Where's bind happening? Okay, so that's even worse. Lol. So let's go to flush. Okay, so yeah, so draw elements is taking up heaps, as is sprite.getShader. Now the other thing that's kind of important to note is that binding our vertex array is taking up 30% of our entire application. 30% of the time for our entire application is spent on binding a vertex array. Yep. I was telling you guys that binding was very expensive. It is. Almost a third of our entire game is spent on binding vertex arrays. We don't want to do that. That's one of the reasons the batch renderer is so much faster. Not just because of the whole, like, drawing everything in one draw call thing, but also because of the fact that it's not having to bind it for each sprite, right? All it does here is bind for every single sprite we have. Yeah. So, that is it. So a third of our time is spent on draw elements, a third of our time is spent on binding, and the rest is spent on, like, 10% is still quite a lot that's being spent on uniforms. Uniforms are quite expensive. Not to mention that the other thing is set uniform. Get uniform location, as you can see, does take up quite a lot. Get uniform location takes up 2.6%. We could definitely optimize this by having a dictionary or a map of our shader locations, of our uniform locations. So we could sort them. The key would be like the name, and then the other thing would be the int, right, or GL int, right, which will be our uniform location. So that once we get this location once, we know where it is for that particular shader. It's not going to change. So why do we need to query OpenGL for it again? Let's not do that. Let's just store it in a cache, basically. So by storing it in a map. So we should do that. We're not going to do that now, though, because that isn't really a bottleneck for our batch stuff right now. But that's something that you could do, and probably something that I would recommend to do, okay? Because part of set uniform, right, is actually, in fact, as you can see, 2% of our entire runtime is the... if we go back to here for a second, actually, you can see that get uniform location is taking up 2.6%, and the rest is the uniform matrix for FV call. Okay, that's taking up the remaining 7%. So that's still quite a bit. All right, and again, these numbers are relative to the actual entire application, not just this, obviously. Otherwise, it would add up to 100%. It doesn't. Okay, anyway, that's it. That's all I wanted to show you guys in terms of performance. Let's try and get the color stuff to work a bit faster, and then we'll talk. So if I go into my Performance Explorer, which is over here, I'll just go ahead and delete these 3 reports just so they don't confuse us. And I did the wrong thing. I meant to actually delete them. I didn't delete them. I just removed them. So in open containing folder, I don't even know where they're stored. Here they are. So that's the actual session. These are the performance ones. I'll just hit delete. Okay. All right. Cool. I just did that not to confuse us. So if we go back here and we profile the batch renderer again. Yes, that's looking good. Let's resume profiling. Yep. So we'll gather a bit more data this time. I'll let it run for about 10 to 20 seconds or so to get it the best. Okay, that's good. Let's stop profiling now. Okay, so there's our report done. So if we take a look at this report now, so submit is taking up the most, we knew that, but what we probably didn't know is, I might just bring this out full screen, is that so color isn't taking up that much. It's taking up about like 0.5-ish. I honestly don't see this as being much of a performance gain. At least as much as this. This one's taking up 12%. Okay, we'll go ahead and do it, and we'll see what happens. So this was our current setup, right? Submit was taking 68.3%. That's all we need to know, and it was running at about 380 to 400 frames without inlining, and about, as you saw, 700 frames with inlining. Okay, so fully optimized basically was running at 700 frames per second. So remember that data. Write it down somewhere if you like. I'll just get the stream to remind me. Lol. Okay, so we'll close this now. So let's go ahead and check and take a look at this. One thing I want to mention really quickly as well is what we did here is in our batch renderer.cpp. I'll just close Performance Explorer. One thing we did in our batch render.cpp was we, I'll try and make sure that the chat doesn't get in the way. In our vertex attrib pointer, we we basically yes, so the way that we were calculating the offset of this was we were just going 3 times size of float. What happens though if we were to go into say this, and maybe, as I said, we would be adding texture stuff, maybe we want to push that down, don't we? What happens is we need to go back here and change everything manually. So instead of that, we can use something called offset of. So let's quickly offset of. Let's quickly just take a look at offset of. I mean, it's pretty simple. The only reason I'm going to this page for you is because I forgot the header in which it's defined in. Okay. C standard def. So this define basically will calculate the offset of a particular member in, say, a struct, for example. Okay. So if we close this and we go into batch renderer.cpp, or .h, I know the capitalization here is a bit annoying, but that's all right. Yeah, let's see, batch renderer.h on my other monitor for some reason. Okay, so if we go ahead and include that, then over here, all we need to do really is, instead of this 3, again, make sure it's in the view. Instead of the 3 times GL float, all we really need to do is be like, I want the offset of the struct, which is vertex data, and then basically its member, which is vertex data, excuse me, color. And that's it. And if we do that and we launch this again, we should see that it works exactly the same as before. Yep, it works the same, but we're now using something that isn't just basically hard-coded, right? It's actually being calculated now properly, and if we move these around, it won't affect anything. Just a quick tip that I wanted to point in. Anyway, we're going to be changing color to a, or at least for now, to a, I'll just comment this, I won't bother macroing it, to an unsigned int, yeah, we'll just go int color. Okay, so what do we need to do to change this now? Over here, we should change this to GL unsigned byte. I know I put int, but it's going to be an unsigned byte. Normalized, I mean, it will be normalized because, oh, actually, hang on a minute. Do I want unsigned byte? I guess so. Yeah, well, so we'll put true here. And then, let's see, that looks pretty good. Okay, and then the major thing that we need to do now is convert this color into something that isn't that. So if we go ahead and say, let's just, okay, so first up, let's extract all the channels. You guys know how to do this, or at least you should. So we'll multiply, so the color right now is in between 0 and 1, right? We want to change it into normal ints. So color times 255 is how we can get it into an RGB thing. And if we want to extract it now, all we have to do is, if we shift it by, so rare, what am I doing? Oh, it's already separated. Lol. What I meant to do was this. Let's go ahead and just go color.x times 255. Whoops, GBA. I think it's actually, I don't even know what the format is. I think it's RGBA, but it's like some other bit format thing, like big endian or something. I don't know. I'm not a big fan of endianness in general story. So anyway, now that we've got this, let's go unsigned int color, or C, because color's taken, and we'll go ahead and I'm going to just believe that these colors aren't going to be greater. They shouldn't be greater than 255 because that shouldn't be greater than 1. So we'll trust it. We'll trust it. So we'll go ahead and we'll say, God, God, I'm gonna have to remember this. I'm pretty sure A is the first thing that comes up. So if I just go ahead and I don't even need brackets. So I don't know. I'm going to just... No, it's not. Is it? Oh, I wish I remembered this. Stream, any help? I don't remember what order the channel is in. I'm just gonna say A. It's probably not. Okay, yeah, that's right. Thank you. Eat, play, hate. So A, B, G, R. Alright, so that should be correct. So if we go ahead and set that to these puppies, hopefully this will work. Yay, it does. Are we faster? I think we are. I unfortunately forgot what the performance was before. I think it was about 400, so we look like we're about 70 frames per second faster. If we quickly go ahead and check with our performance. So analyze, profiler, start with profiling paused. Yep. Gather your data. Alright, stop profiling. So it was like 68%, I think. Right, stream, remind me. I asked you guys to remember it for me. Well, it's like 70%, so that probably wasn't a great indication of stuff. But we know that we were 700 FPS, and yes, it's because of CPU caching and whatnot. It's probably not the best idea to actually rely on that profiling data for that particular thing. So what we should do instead is, yeah, it was like 360. So it's like 100 frames per second faster apparently. So let's go ahead and just. We know that it was exactly 700 before when we had inlining. So if we change inlining to any suitable, we recompile all this stuff. And we take a look. Hopefully it'll be above 700 FPS, and we would have done our first real optimization. So cute. And I see an 8 there. So, wow. Look at that performance boost. Almost 200 frames per second faster. See that? Amazing. In fact, it's more. It's growing. That's weird. That's suspicious, but okay. It's growing. Anyway, 920 frames, it looks like. Oh, it's dropping. Yep, no, 920 frames. Are you guys amazed? I'm amazed, personally. So anyway, that is going to pretty much wrap up this episode because I think we've done a lot. Before we go, though, I do want to show you guys how these episodes will run from now on. So this was like a maintenance kind of episode, but we didn't really do too much maintenance because this took up more time than I thought because I had to introduce you all to profiling. But the point is, on my GitHub account, under Sparky, under issues, oh yes, that reminds me, I should fix something. This is where you can open up issues. So if you go ahead and click new issue and you just anything in Sparky that displeases you, usually bugs and stuff, not just something like, oh, I think this should be like, yeah, you know, honestly, anything that you find is an issue in terms of like, you would rather have it this way, or you tried to use it and you're like, maybe it should have this kind of usability, whatever, open up an issue on GitHub just anytime, and the next time I do one of these maintenance / optimization episodes / bug fixing episodes, which will be every 10 episodes, I will take a look at all of these issues, and I'll basically go through them and make sure that they're basically fixed. So the first one, which was submitted by Fatality, was including battery render 2 times in main. One thing I want to quickly mention, and I think I was doing that, I remember seeing that when watching my own video when I was editing it. Yep, battery render twice. That should be there. One thing I will point out though is anything in main. One thing in main that should we say fixed in episode 10. One thing I should say that's probably important is anything in main, do not take it too seriously, okay? In fact, don't take it seriously at all. It's basically a joke class. It is literally, it's a joke. Because, like, for example, allocating so much memory for new sprites, but I'm not even deleting it at the end. Lol, why are you doing that? You're a terrible C++ programmer, etc. I don't want to hear it. This is just a main class. This is not part of the engine. That's why it's not even in the source directory, right? It's just a main class. So just in the future, nothing in here is an issue. Okay, you can totally open it up as an issue, but don't see it as an engine issue because this isn't part of the engine at all. It's just a test class. So obviously, I'm not going to spend time on making sure it's good because it's not part of the engine. Okay, it's just there for testing. All right. Now the other issue was actually me. I opened up this issue. But basically, mat4 multiplication doesn't work correctly. Okay, one way we can test this is by, say, rotating everything. Maybe just translating it, rotating it, doing a bunch of crazy stuff with it. So right now, well, you know what? We could probably say this will be interesting. Okay, easy way to do this. Let's go back into. In fact, we can just do this here. Okay, so. I don't know, if we have, say, a matrix. So we'll call this mat. And this will be maths, mat4. Oh, I don't have to use the maths namespace, do I? Wait, do I? Yes, no I don't. Okay. So, translation, and we'll just go vec3 5 5 5. I don't know, then we'll rotate it around that pivot point and then we'll translate it back, for example. It doesn't really matter. Mat times angle. Okay, so we'll have to actually do this live. And by live, I mean in here. So we've got our time. So time.elapsed divided by whatever. I'm not actually going to make this time like a timer. I don't care. And then the axis will go z-axis, which will be in like a kind of 2D rotation. All right, so if we do something like this and we go ahead and say shader.set uniform mat4, let's just see what happens here. Nothing. That's fantastic. Why did nothing happen? That certainly exists. We're in our good renderer. Why did nothing happen? That's weird. Where are our shaders? Model matrix. Oh, my timer is too slow. Yes, that is also something that could be the case. So where's main? Main is gone. Oh my goodness. Where did you go? Okay, let's probably. Okay, that is weird. Wow. Well, as you can see, rotation is working perfectly. If we just had rotation, I think it would actually be working. So let's try that. Okay, that's not even working. Okay, now I'm suspicious. Oh no, it is working. Oh, it's so slow. I don't like those artifacts though. They look weird. Times 100. Okay, cool. So that's working. It's rotating around that point. I'm pretty okay with that. I mean, those visual artifacts are a bit annoying, but that's for another episode. Now let's try some kind of multiplication. So, mat for mat equals, I wish I hadn't deleted everything. Let's just Control-Z it a bunch of times. Okay. Alright, so as you can see, it's rotating in more than just the Z-axis. Something is up with this, so we should probably fix it. And luckily, I already fixed it, so this is the solution, as you can see. Basically, what we were doing is we were setting the elements directly. We need to basically put them into their own array, and then we can just use memcopy to copy them, okay? So basically, if we go into mat4, which is under maths, mat4, we'll go ahead and make a float called, I'll just call it data like I did in the other thing. Instead of sum plus equals element, no, this stuff is obviously here, but instead of us setting elements to sum, we're setting data to sum, and then at the end, we're just going to use memcopy to copy. So our destination is elements, our source is data, and the size is going to be the size in bytes. So it's going to be 16 because that's all. We're going to do 4 times 4 times the size of float, which is what these are stored in. Okay, so if we now test it out, hopefully it will rotate properly, and you can see it is. So it's rotating around an origin of like 5, okay, which is what we're telling it to do. Okay, cool. So that is a quick bug fix that I wanted to implement. Everything else looks pretty good. Again, if you find issues, just post them here and I'll fix them in the next maintenance episode. All right, cool. I don't think I missed anything. So if you guys enjoyed this episode, please do not forget to hit the like button, and I'll see you guys next time with episode 11, in which we'll probably be doing layers. Okay, so our next episode will plan out the next 5 episodes. So I'll see you guys then. Goodbye. Vroom.